All right, so we are now ready to find out how to find the equation of this line right here. And so back on my writing board here. So first of all, anytime you're on a scatter plot, then this line represents, or this line is called the best fit line. Or the best fit line, or many people also call it the regression line, or there are quite a few different ways right here calling that. I tend to call it the best fit line right here. And then regression line, but it's all indicating to the same idea. So before we get started, keep in mind that one thing, that the whole purpose of the best fit line is not to aim at it's not the line aiming at containing all these points to be on the line, but it's just simply the line that makes, you see, that's why I like to call it with this name the best fit line right here, but it's aimed to be the line that have as a whole group of points here, then it's the line that makes the best distance in the sense that every point from the line here, each point is making the least distance. And of course, I mean, some points are still far than some other point compared to the line, but it's the best one of all lines here. Because think about some line, if some line contain these 2 points and it leave everybody out, so we can find one unique best line that it makes the best distance, the best minimum distance from every point right there. And like I said, it's about the best the line can do. And so let's draw a different line right here from scratch again. But in the end, a line, anytime we're looking at a line right here, the line has an equation. And that famous equation for any line here is the equation y equals mx plus b. And of course, provided that we're putting the x data as a variable on the horizontal axis, and we're putting the y data as a variable on the vertical axis. And so in that case right here, once again, famously, any line is known to have equation y equals mx plus b, where a quick explanation here is that the m right here is the slope of the best fit line, the slope of your line, and this b value is the y-intercept. And so, as long as you're now ready to find that the line of the equation of the line right here, then the only thing we are expected to do anytime that we're coming up with the equation of a line is to find out how big the slope is and what's the y-intercept of your line, and that's how we're done. And so, gladly that finding slope of the best fit line in statistics is not as challenging as the way how we find the slope of any other line back in algebra courses. But here we have one unique formula right here, that the slope of your best fit line is found by the correlation coefficient that we calculated previously, and then we're going to multiply with the ratio of s of y over s of x. And so back to our data. Let's quickly have a look at our data again. And it's that one same data we've been starting since the beginning of this particular topic here. But so this data, we have found that the correlation coefficient after the running the linrect command right here, and it gave us that value in precise, in 5 decimal precision, 0.84425. And so now immediately, just now we learned about the formula for getting the slope. So what we do in here now, according to that slope formula, then we have this correlation coefficient, 0.84425. I am going to multiply and recall that the SY that we used was a 0.14, and the SX we found the standard deviation on the X list was 3.6. So now calculation shows 0.03283, and that is how we calculate the slope. of the best fit line. And now, so the y-intercept is actually found by the b value that we've had right there. The formula here now is going to be y bar minus m x bar. And so now, congratulations, we've made it through the two important formulas for getting the equation of the regression line. And so immediately bringing that into our best fit line, into our data here, then our current best fit line turns out having y-intercept b equals, our y bar value was 0.67, and our slope we found here previously 0.03283, and multiply with the x bar that we had in the data list was a 9.43. And so now we are ready for getting a final calculation for our y-intercept of the regression line. It turns out being 0.36041. So those immediately in our example going parallel with the lecture here, then we found the slope and the y-intercept of your best fit line equation. Now, so I have to clarify one thing, but for viewers out there who are not in my class, who are not students of my class, then really you have a lot of ways to approach finding the slope and the y-intercept of the best fit line equation. So for example, recall that when we run the linrec command, so when you go to stats, use the right arrow key and turn over to the calculation and select option number 4. And then once again, recall from earlier of the lecture here that I put my x list in L2 and my y list in L3. Then we're going to hit enter a few more times. And then finally let it run. And so now, after we actually did the calculation of the slope and the y-intercept of the best fit line by hand right here, if we now look back into this menu that was given out to us earlier, then we actually notice that the calculator we have here is actually now strong enough to calculate. So here's the slope that the calculator already calculated for us here, the slope of the best fit line, and you can easily also obtain the y-intercept right here. Microsoft Excel users can also, the trick here now is that right from when you created your provided, you know how to put up a scatter plot. So simply just right click on any of your scatter point right here, and there's a pop down menu that says, and then somewhere at the bottom of near the bottom of your popped up menu, there is a line that says, there's an option that says add trend line right here. And then when you go to add trend line, and I'm using an old version of Microsoft Excel, but the newer version should work pretty much the same way right here. Make sure in Microsoft Excel you select linear, and so now display equation on chart. I haven't done that throughout my lecture, but here I'm also going to display the equation on the chart right here. And so, and then let me put the equation in a little bit larger print right here. All right, and so if you can compare it, and both TI calculators and the Microsoft Excel gave out the same result, and it is these results right here. This result came out from technology is slightly different from our result that we did through the calculation. Now, so here's a one note specifically for student of my own class here in Math 256 that I actually do expect my student to use a formula to do the calculation of the correlation and coefficient. The reason being for this is I want my students to have that ability to, once you accept a rounded value, then you're going to be responsible for your own calculation and then use each of these values for the next calculation. And so I just want my student to have that ability to retain and be responsible for their own calculation, and whatever they make the decision, and it does slightly change the precision of their final answers a little bit, but that's okay. We don't need to, in my philosophy for my students, we don't need to compete with machines right here, but what I need them to do is to have that ability to be responsible for their for the work that they decided. And so back into what we are doing here and almost finished. So we're now actually ready to conclude our best fit line equation. So the equation now is y equals, we got the slope value ready. So 0.03283 x plus, and then the y-intercept here is 0.36041. Okay, and so here's the one thing. So now this is the one thing that I've been, if this is an actual class, I've always been making this joke with my student, and it's actually the truth here. There will be no technology knowing how to do this, but we are a human being. We know how to make this clear and making us different from the machines right here. Please put hats over the variables of your best fit line equation. So the first number one thing, and you will get that explanation shortly as I wrap up with the lecture later on. But so here is my best fit line equation, and then the only thing that I need to add to your understanding, make sure you put hats over the variables of your equation. But this is our final equation of the best fit line. And then so let's quickly recap before we move on a little further. But so what we did first, the first calculation we actually did was to calculate the correlation. And then once we had the correlation coefficient, so to remind, this is the correlation coefficient. And then once we got the correlation coefficient, then the next step we're calculating is actually, we were able to now find the slope, because having the correlation coefficient gives access to the slope right here. So the slope formula depends on the correlation coefficient in the formula that I'm giving right here. And here it's sy over sx. And then once we've had the slope right here, then the y-intercept of the correlation, the y-intercept of your best fit line is now actually going to be y bar minus m x bar. And so we've made these two formulas. And like I said, again, that for a student in my actual class right here, I do expect them to be able to use the formula for the calculation of these values. We only use the linrect command to obtain that precise value for R right there. And then the final best fit line equation concluded to be y hat equals m x hat plus b. And that's how we complete our best fit line equation. All right, so now it's time to answer those questions, sort of like why hats? Why putting hats over our variable? Like say y hat and x hat are here. Just why? Why not using the traditional or the plain old variable x and y? So here's the reason why. So for now, at this point, we came to the equation being y hat equals 0.03283 x hat plus 0.36041. All right, and so here's the reason why we're putting hats over our variables right here. So let me raise this question right here. And seriously, throughout the whole time, we've been doing a lot of calculation, but none of that has been put into some good usefulness yet. So here's the whole purpose of why we come up with the best fit line equation. Say here's my first question after we come up with the best fit line equation here. Let's say I'm going to say if, and of course regard to our data that we're still currently using. So if x equals 8, and my question here is simply find the y value, or I could also use a lowercase letter here. It makes no difference. Right? So if x equals 8, find the y value. And so the questions a lot of time think about the side of the person who asked. They don't really need to get it too detailed for you. They just simply, hey, here you go, x equals 8, x is 8, value 8, find a y value. Answering this question, and by the way, hopefully you can spend, or you can pause the video a little bit to have one more look into the data that we've had on my Microsoft Excel here. But then when it gets to this question, actually, we got two ways of answering it. One way here is that, what's the whole point of coming up with the equation? So yay, bingo, go ahead and let's start using it. So having x equals 8, I'm going to simply substitute x into the equation. So here I have y value and the way it is. So for now, I'm not going to worry about hats, because I'm also trying to promote a problem and explain why we're putting hats over the variable. So let's say for now from scratch we just pretend that we ignore the hats here, but having an equation is useful. I'm going to substitute 8 into the equation. So here I have 0.03283 multiplied with 8 plus 0.36041, and then calculation shows y equals 0.62. And to make it relative to the kind of data in our particular data on the Microsoft Excel here, so each of these values are going in 2 decimals. So I'll just stay with 2 decimals in my final rounding of y. So that's one way how I calculated my y value. So we thought we found the answer. And by the way, let me just remind again, the way we obtained this y value was to substitute the x value given into the best fit line equation. But now, before I even proceed into doing this, there was already another option. If you notice that, so now once again, have a look into the data. The data itself here that we're looking at does indeed have the value x equals 8 on the data, and then the y value that was recorded corresponding to x, the y value recorded here and came together with the data with the x value 8 here, that y value there was being 0.53. So now all of a sudden we found out that there are 2 different ways of answering. And so now I'm actually going to try to explain the difference between these 2 answers right here. So the answers that came out by using the equation will permanently remain as this is a prediction. It's a predicted value, or for shorts, it's a prediction. And that also, ladies and gentlemen, that also mentions about the purpose for coming up with the best fit line equation. Anytime you come up with the best fit line equation, the entire purpose of that is to predict those the data values that are outside of our data point, and we will get to that explanation a little more clear later on. But this value here now, the other y value that we actually read it out from the table, this y value is actually formal term observed value, or it's already an observation. And so in this kind of question, by default, observed value is being preferred. So in case that one question having that can possibly lead to 2 different answers here, the question here does refer to the default observed value if we can have that value available. And so in statistics, we reserve the plain variable's names, just the x, the y without hats, to indicate these are the observed values. So if you one more time look into the data table over here, so any of these values, if we need to indicate them, then this is x, and this is this is y equals 0.75, y equals 0.68, y equals 0.78, and so on and so on. But these y values are the non-hat values. Same thing here, x value, x equals 9, x equals 8, and x equals 10, but these are all the plain x, the non-hat. But anytime we come up with a value that came out through the calculation using the equations, that value permanently, like I said, remains as a predicted value. So here we have to put hats to indicate their purpose. And so now the explanation to why we're using hats in our equation here is to remind anyone that anytime you're about to use this equation, its only purpose and the permanent purpose is to use the equation and come up with prediction. So any value for x or for y that we answer coming out from this equation only remains as a prediction. And so now I'm starting to talk along that line where we're doing the prediction. And let me bring up a different question right here. So now let's say I'm going to have let x equals 12. Find y. And so similar to how I explained with the earlier questions, by default, we're going to look into the table and see if we have x equals 12 anywhere, because observed value would be by default the preferred choice of answering this. Because the person who asked doesn't care from your side if whatever you have right here. So if you have a real observed value, then provide that to the person who asked. But however, in this case, x equals 12 is actually nowhere found in the table. And this is where we're forced down. The only choice we have left is to give a prediction. And so that's where now the only choice we have for the answer, y hat equals, so now 0.03283 multiplied with, hypothetically, if x equals 12 was there on the table, then we can multiply 12 with the slope value and plus with 0.36041. Okay, and so now I predict that the y value should come out being 0.75. And so now the tricky part about answering these kind of questions is that it's us who are the person who gives the answer need to be able to decide in which case, which situation you can give a good observed value, or in which situation you only can give a prediction. And then there are the other kind of questions. If now y equals 0.75, or maybe I changed my mind, let's use 0.68. Let's find x value. What's the x value? That's when y equals 0.68. And so at this point, once again, you can kind of see that here, when we're looking it up into our table, then we actually do have an observed value for 0.68 right here. And 0.68 on the table is corresponding to the x value being 10. And so here by default, I'll just give the observed value x equals 10. And this one here, we give our answer as the observed value. And there's no need to worry about the prediction, because here, like by default, this value here does appear in the table. So let's go ahead and directly find the observed value correspondingly to that. But now, if the question says if y equals 0.8, and once again asking us to find the corresponding x value, then 0.8 here is nowhere located on your data table, in your table given in the Microsoft Excel screen right there, then we are forced to use the only one choice left, use the best fit line equation to predict what should come out for the x value. So in this case, we're going to pretend, or we're going to hypothetically say that 0.8, if it was there in the data, so it's going to substitute on the left-hand side to the left-hand side of the equation, 0.8 equals 0.03283 times the unknown x that we're predicting plus 0.36041. And so now what we all certainly realize here is we produce for ourselves a linear equation to solve for. And so taking the 0.36041, subtracting that from both sides, and we ended up with 0.43959 equals 0.03283 x bar. And the last step here is just the standard solving equation, dividing both sides by 0.3283. 3283. Now allow me to write the variable on the left hand side, and my calculation shows x hat here is equals to 13.39, or actually we don't need to round here, so 13.39 is about the best here. All right, and so once again, this answer we came up with, it came out from the equation of the best fit line, and it permanently remains here as a prediction. We predict that when y value equals 0.8, we can predict that x value should come out being 13.39. And so the entire process since we began our lecture up until now start out with finding step number one, or the stage number one of the process here was to nail down the correlation, or to calculate the correlation coefficient. And then once we've had that, and once again remind yourself this is the lowercase letter r, and the next step down was to come up with the best fit line equation. It's the best fit, and here we were using the line equation, and then sort of like it produced the two little sub steps for us. We're here, the two sub stages were here for us, that the slope was r times sy over sx. And then once we had slope, then the next step here was to find the y-intercept, b equals y bar minus mx bar. So these are the two formulas that we've learned previously in the formula. And then once we came up with that, then once we got slope and the y-intercepts, then we came up with our final concluded linear regression, or the best fit line equation was y hat to equals mx hat plus b. And then recall from what we done after getting that equation, was we were able to, so the next big stage here were, after getting the equation of best fit line, we were able to make predictions. So the whole purpose of coming up with that best fit line equation is to make predictions. And I would say a little strong word here, but of all kinds. All kinds of predictions. Predicting for x value, predicting for y value. And so the entire process here, the entire process from the beginning steps, that was about getting nailed down your equation into at the point, a certain point where we successfully got our equation of the prediction and use the equation to make predictions. So the entire process always go in that certain order over here, from beginning to the end down. So you can see I'm drawing my down arrow. So the process like that is formally called the regression. It's a regression. And then particularly that we using, so being able to come up with equation to make prediction is called a regression. But then what we learn here at the level we're learning here, and one day when you go to a more advanced course in statistics, you will learn a different method here. But here we use a method that rely on the line right here. We are using line equation model right here, and so that's the reason why our topic of discussion here, we refer to this as linear regression. So because due to the fact that our steps here on all that work from getting the correlations and getting down to getting the equation of the best fit line, we refer to that as a linear regression. So now after finishing with what I just explained right there, then that actually opens up a couple other options right here. Somebody, after viewing this video and hearing my explanation, you're going to start wondering, so that means outside of linear, because algebraically the line is not the only equation we have. The linear equation is not the only equation we have. So will there be time where we making a regression, a prediction model that use a quadratic? And yes, there are. Admittedly, there are times, even though not as commonly used as the linear regression, but there are times that we use a quadratic model. And so, of course, guess what? That name there, we call it, it's a quadratic regression. Even the people in these days, in the modern day, come up with exponential regressions. There are also logarithm exponential regressions. Let me quickly show you that. You see, when I was opening my Microsoft Excel screen right here, and was opening up that dialog box to add the trend line right here. See, look among these options right here. There are polynomial regression. There are the one we use here is the linear regression. There are exponential regression, and there are so the quadratic regression was among the polynomial regression right there. But back to the student who are viewing this, then your level that you're learning here, we only need to focus on linear regression right there. And it's gonna have to wait until a much further course in a university, a formal university level, to learn about all these quadratic or exponential or logarithm, or not, or until some of the time that we're doing nearly the graduate course level.